Okay, are we live? Are we live? Let's see. Let's find out. Can I hear myself? Oh shit, I can hear myself. Let's find out. Can I hear myself? Okay. The audio is dog shit. That's chill. How do I share this? Where do I go? This? Open? Cancel. If we go through dog shit. It's so old doing this. How do I share this? Did I share this link? Where do I go? If we go here, what happens? Oh, cancel. If we go through. Look at my channel. Mute this. Turn down this. Turn up that. Go to my channel. Live. Video link. Okay, here we go. Now I need to open my messages and not have it show up on my main screen. Okay, there we go. Okay. Alright. Time to. Okay, what are we doing today? We're doing research today. I have like probably about an hour and a half to crack this out. I probably won't get much done, but it's gonna be a process. So where do we start? Okay, today we're doing particle filtering for Monte Carlo EM. Monte Carlo EM. So why are we doing this? Okay, so high level my research, right? We have a diffusion-inspired language model. All this means is that the language model, instead of generating a sentence as like I saw a dog, right? Instead it might say, right, so like normal autoaggressive. Right. Generates the sentence in one path, right, left to right. Just one slow pass from left to right. Non-autoaggressive language model is anything that doesn't do this, right? So maybe instead, in one step it says dog, then it says saw dog, then saw happy dog, and then maybe like I saw a dog. Right. Each one of these steps, might occur in some opaque process. The whole point is that this language model is able to make these like revision passes over the same sequence multiple times. And how does it do this? Well, it does this by predicting edits, right? So like to go from dog to I saw dog, a plausible edit sequence might be insert I, insert saw, copy one, right? Where copy one implicitly, like this token here, is inserted by copying the first token in the previous sequence. Alright. And then maybe we go from I saw a dog to I saw a happy dog. Insert or copy one, copy two, insert A, insert happy, copy three. Alright. So like this happens at the token level. So again, we go from I saw a dog to I saw a happy dog. We copy some number of tokens, we insert the new ones, and finally introduce the very last type of edit. If you go from I saw or simpler, happy dog to joyful. Typing when Like I know no one's watching this, but typing when I feel like there might be someone watching is like scary. Like I feel cold right now. Happy Dog and Joyful Dog might be, sub 1 for joyful, and then copy 2. Okay? So these are all edits. So we want to train a model to predict these kinds of edits over a long sequence, right? And there's some architectural differences in the way that we design Evolver, which is the name of this model that differs from traditional language models. And some of the ideas are like wait time sharing, like parameter sharing. But those aren't really relevant for today, or what I want to do in this next hour. What I want to do in this next hour is basically implement a new idea, or even just flesh out a new idea for how this is going to work. Where it's like, okay, I have supervised sequences. How do I supervise? How do I train, right? So like, I might have this entire corpus of examples of going from dog to happy dog to I saw a happy dog to me and Jane saw the happy dog, right? I might have this entire corpus, but it's not immediately obvious like how you train the model to properly learn to generalize to create these revision passes in the previous sequence. Obviously, there's many ideas. In the literature, there's a lot of similar, like iterative refinement or diffusion-inspired language models, and all of them really go about training in very unique ways. Some of them do imitation learning, where they sample some roll-in, and then they learn to imitate some expert rollout policy. Some of them just do force alignment, right? So that you say there's only one way to go from A to B, and you're gonna learn A to B, right? Like that's how you would train on the regular, like a normal language model. The problem with that idea is that number one, you need to know what is like the correct way to go from A to B, right? And it's not always immediately obvious like what the best alignment is between two sequences. Secondly, forced alignment runs into these issues where basically the model doesn't actually learn the repercussions of its actions, right? Like, say I have a sequence of actions A to B to C to D to E to F, right? And I train the model on this sequence and I say, every time you say A, go to B. Every time you see B, go to C. When you see C, go to D, right? This is great, like this can work in training, right? The problem is that when you put this model out in the wild, it's always going to make mistakes, right? Like that's inherent, right? Like you're going to make mistakes like no one does, right? And so instead of going from A to B, the model might go from like A to B plus epsilon. Where epsilon is some like small error, right? The issue now is B plus epsilon never showed up in training. And so now the model's like, oh shit, I've never seen B plus epsilon. So maybe B plus epsilon was kind of like C, but now I have this extra noise. And in my guess, right, oh, maybe I'll go to C plus 2 epsilon. Right? And you can see where this is going. It's basically the problem of compounding error, right? It's like, it's like your whole life, you go through your whole life only learning to do things one way. You go out in the wild, you try and do things your way, but something unexpected comes about, as it's bound to happen. You make a little mistake, and then the more mistakes you make, the more out of distribution you are. Therefore, the worse your performance is, right? And there's a result here, right, about meditation learning where you just do normal supervised training. You have, some quadratic bound on, or maybe it's like a quadratic lower bound on the number, on your error amount, which is, obviously not good. But I mean, that's kind of a later issue. The current issue right now is we do want to do kind of a supervised training, and like we tried this already, right? We say like, if you want to go from dog to I saw a happy dog, you know, previously we thought like, okay, there's only one way to do this, right? The new idea is that me and Professor Eisner discussed yesterday was maybe we let the model basically try things out and then discover on its own like what is perhaps the optimal way to do this on its own. And the idea here is expectation maximization. So, oh man, can't type right now. What is it? What is expectation maximization? Well, say you tell a model, okay, here's all these supervised sequences. I want you to maximize the chance of you being able to recreate this yourself, but I won't tell you how. Basically, make the model guess how to make it, right? And then, based off its guess, you get into the model, oh, your guess is actually pretty good. So, make your guess more likely, and then guess again. And then do that again, and again, and again, until that converges to some local minimum, or maybe the global minimum, you know, that gives you some kind of lower bound that's suitable for your problem. It might seem weird, right? It's kind of like eating your own shit. It's like you tell a little kid, right? Like try making some food, okay? And the food you're making is really bad, but after you make that food, I want you to make that food better. Well, okay, it's not a good analogy because that actually makes sense. But basically, somehow, right? I mean, not somehow, right? Like, mathematically, this happens, but somehow, this iterative process has some nice convergence properties. It's actually a variational method, which means that we basically have this nice lower bound on the likelihood of our supervised sequences, you know, with the beauty of Jensen's inequality, all that stuff. Very hand-wavy, you know, and I'm not sure really recall how that stuff works. But yeah, where am I going with this? Okay, whatever. That is EM. So what does EM look like for us? EM for us looks like, okay, one, take a bunch of supervised sequences, make the model guess. Okay, I don't want to say guess. Make the model tell us the distribution over plausible edits between sequences. Backprop over that distribution of do 2 and 3 a bunch of times. Well, I really can't. Okay, I really can't type right now. It's actually really embarrassing. I'm getting like Vim state right. Oh shit. Oh shit, I got weird. Okay, whatever. Now I'm actually nervous. Now I'm actually tweaking. So what are we doing here? Okay, sorry. Let's stay locked in. I actually want to go until like 9 and actually flush that. Actually, maybe I'll go longer. But now I'm like nervous. Because I got shits watching. One of these messages from, let me see. Get it too kind. Okay, let me think again. So the problem here that's challenging is, number one, it's difficult to actually, okay, it's computationally difficult, but also difficult to extract from our model. Like, the exact distribution over all the plausible edits for every pair of sequences. And it's also not immediately obvious. Well, maybe it is, right? Maybe there's some weighting strategy, but it's not immediately obvious how you backpropagate over the entire distribution. I think the way you do that is just by weighting. The problem there is that it's totally intractable because you can imagine actually between sequences A and B, you actually have like an exponential number of plausible edit sequences between those two, and so we're backpropagating over this like exponentially massive set of sequences, right? So regular EM doesn't work because exponentially many sequences. And so the idea with Monte Carlo EM is approximate EM by sampling from the posterior distribution over edit sequences, how to get posterior. Okay, so this is what I was putting up to. How to get posterior particle filter. So this is the classic, we're dealing with Bayesian like inference here, like posterior approximate inference here, where it's computationally very, very expensive to get the exact posterior because of the exponentially large space of all plausible edit sequences, which is any two sequences, let alone over it actually might be like extra. It's actually like extra exponential. Because you have exponentially many sequences going between two sequences, but also for any edit sequence, you have exponentially many paths going up and down through the fusion step. So it's almost like you have an exponent of an exponent, which I remember my complexity theory would probably be bounded by something. And maybe that's like whatever. It doesn't matter. The point is that we don't want the exact posterior. What if we have posterior? It's probability of edits given model parameters, basically. Very, very large denominator. Approximate by MC sampling. So like what is the family of like Monte Carlo methods? Right, really, it's just you have a distribution that you can like kind of sample from, right? Or maybe not. Like maybe you have. I mean, really, this is like MC, Markov chain Monte Carlo, but you have some challenging distribution that you can't directly sample from, either because it's too big or it's too whatever. So rather than directly sample from it, you I don't think I can explain it very well. Well, I mean, this is what I'm trying to figure out today, actually. How do we sample from the posterior via particle filtering? Okay, so let's talk particle filtering. Okay, so I think we're doing something like this actually today. The idea is this is kind of like beam search, right? This is kind of like beam search with pruning, where we have some set of particles, right? The particles are our samples from, like we have some approximate samples from the distribution, or maybe from some proposal distribution, and we want to basically go through this iterative process where we slowly transform the particles so that they become closer and closer to our target distribution, where the target is our cosphere with a model parameter. So what is that proposal kernel? Well, the proposal kernel is the local distribution. The proposal kernel is the local distribution. Okay, so basically, edit step, you have some roll in, right? This is kind of like our alpha and hidden Markov model. You have a desired token and a rollout. Wow, I really can't type. And there's n plus m plus 1 total option. N plus 1 total options available from in the trellis. Branching after leading trellis. Where it's n ordinal stubs. Copies, always going to insert. And the reason this is a proposal is because the actual distribution looks like the local operation probability times the beta probability, which is the rollout sequence. But because the rollout sequence is dependent on our roll-in and our local choice, like we don't have access to that. If it were like a hidden Markov model, then we could use the forward-backward algorithm to get the entire beta probability just through dynamic programming. But we can't do that here because we don't have the Markov property. It's actually a huge pain with our method. Losing the nice first-order Markov property really harms the efficiency in many aspects, like bothing, decoding, training. Even now, not having the Markov property makes things really well. Okay, I guess like for decoding at the sequence level, we never had any positional independence at all because it was always just an autoregressive decoder. So I don't need paper for this. I wish I could draw this. I probably could. I don't think that's worth it. Okay, before actually, I don't think I'm getting very far right now with this. I need to read part of the programming a bit more. I know, okay, we have our local proposal distribution. Simple from those, at each step we have an estimate of our probability mass by reweighting, and then we use some heuristic to resample outside of some top P% of the probability mass. So that way we always have the majority of our samples coming from the highest probability samples. The highest probability samples. Yeah, I just I'm gonna focus. Okay, so step one is like our individual particle drawing from the dynamically computed input embeddings to get the local distribution over possible edits. So that's just always three options. So that's this proposal distribution. So the proposal is just the local probabilities of each individual edit, or I guess all n plus n plus 1 total edits that are possible. And we update the weights. Really like it. Really like it. Okay, so we also have to what's my refactor? So the optimizer what's that actually? So what I'm doing right now is I'm just refactoring some of my training code to make this a bit more reasonable. Tag source. This. Passing logger too, I guess. Do you want to do that? I guess so, because we're calling this from our run file. So we're gonna get rid of this. So we're probably passing the logger. I don't want to like this code, but passing logger is a crazy pattern. That idea is in the same process. I don't know how I feel about having dot forward be like an implicit call in Python. So just extending each other this first roll. Let's do this. Do that. And this should just run as normal, hopefully. Step take 6, they're passing in. As normal. First time, first try. Okay, beautiful. So we also need a target cache here. I don't want to do this whole thing. So this one coding is not very expensive to balance with that. So we can probably leave that. Is this really even expensive actually? Oh, I guess we have these feed forward parts here. And then we look up table. It's not really ideal. So the target cache is just the previous step target. So we only need the targets, the current steps. So we need to pass in also actually or just an index I. The problem is this is across the entire batch. We'll return the target. I need not do this right now. Actually, that's fine. We don't have to do this right now. We can do this later. Initialize particle. Things. Like in principle, we could do this across the entire batch, but and like yeah, that would definitely be more efficient. I mean, that just seems so difficult to manage the entire batch as well. So I guess we'll just make this not batch at all. And I mean, I guess this way also we can not worry about the particles as vectors, but just as our tuple representation here. Steps in C1. Sample next step. Sample. And then resample here. according to re-normalize weights, compute the sample size, and then resample below threshold. So threshold is going to be a proportion of the number of particles, or the ensemble size actually for n. And ultimately, so sample from finite distribution, turn the sample. Oh man, this is just like so slow though. Yeah, I mean, in principle, okay, doing this in batch, what would that even look like? Actually, I guess doing it in batch isn't too hard. If we only worry about parallelizing. Yeah. So doing it in batch means we can parallelize the forward paths. Obviously, the whole pane is gonna be dealing with the path tokens and all that, and so it's like not even immediately obvious to me whether that's something that we want to do. I mean, on the other hand, our forward path is already written with batching in mind. Really, all this means is we tokenize, we convert. Do not also mean we convert. So I'm just so like embed and feed forward. So embed and feed forward. Even this other particle is just fine. Well, I guess the particles I'll start at inserting one actually. We batch. Ignore add. Okay, so maybe we just don't worry about batching. I mean, I'm just trying to figure out if it's going to be worth it or not in the end. Or how much that we're going to accumulate here. Because the forward pass, I guess forward pass is, I mean, we're just wasting GPU cycles if we're not going to batch this. Good idea. Okay, I guess we need to. So when that's up, we also have to compute pause and edit as well. I'm going to do this. Filter by ID. Maybe I table this whole filtering thing. I mean, like, I mean, I have a pause. I mean, I just think this is so painful. I mean, just knowing how long all this took me to figure out, both in terms of like, I mean, okay, so what I'm gonna do is table this for once I write it in the paper. I mean, this is gonna take so long. I mean, yeah, this just seems fucking hard, to be honest. I mean, what can we do on right now? Sub operations would be fine, but we're not really. I mean, I guess I have to do that before tackle particle filtering. I think the particle embedding count is really long for me, though. So, I'm gonna figure this right now. Oh look, nice. So all targets equals 47, and so our B. Okay, so our B is going to be like 10. Our batch size, we're just going 4 for now. max 1 equals 10. And this theory, so E max 1 5, right? Zero. So this is gonna be should be max 1. We want just the batch size, so op IDs that equal 0, indexed at ith column, so 0, right? Perfect. So we need the entire memory, we need all the edit targets. Obviously we want the free target. And also the instance. What I've been liking to do recently is something like this. The lambda function, so all these are going to be IDs. I need this, we're going to take the argmax. And then we want the ith column. Yeah. Minus here. This. Target. I guess we can modify some posts actually. Yeah, so we still do the sweeping positional encoding because I think that's pretty cheap. Same at the end here as well, too, I guess. Did we do that? Let's bring us to passing the index into the forward pass. Is Tash normally done by just yeah, I mean, I guess what I can do is just stack add iteration. So let's make it now. I just really hate these really big and ugly function signatures. I'll add that sometime as well. See really fucking annoying, I think. That just feels clear to me. Leave with target. It's small stupid change, right? It's the most idiomatic way to merge these together. I guess in the outer loop, I can just call it the cache target I times. That's stupid. I mean, yeah, that's stupid because then we're actually losing the whole parallelized aspect, which. I mean, do we even need this right now? Like, I guess it's more for inference. Obviously, it speeds up training by a ton. Is this even slow right now, though? Oh, man, why am I even doing this? Let me think. Temperature, key value cache. Yeah, maybe it wasn't a good idea to do this. I'm just looking for it right now. Append the target. I mean, yeah, we definitely need the target. Mesh on the model. Insert mask. Let's just do this. So max line. Okay, so yeah. Okay, so insert embed is going to be for the insert mask. Does this just work actually? Because this is B. So going to the insert mask is along the back, so it has to be like this as well. I think this actually works maybe. Where does token IDs come from again? Token IDs. Oh, I see. Yeah, token IDs. Token IDs is going to be and like 20, which is the vocab size. We got these equals argmax, so target. Not to mention, this is also going to be, this is the max line as well. So when we get the insert, which is the batch dimension, and the index. So like look at the insert mask is going to be also like subset of the line, right? That's awkward. Yes, it's actually perfect. Oh my god, actually perfect. We're cooking. And then along 0, it's like that curve is, I think. Or 1. Like this. Insert mask along. Definitely mentioned, right? Perfect, okay. So that should be correct as well. And then finally the target. Insert mask is in the batch dimension again. Along I. And equal to our insert embedding, so that should be correct as well. Okay, so that's actually all we have to do. I think it's similar for copy, but we have some like tensor block magic to how I implemented this. Again, this is efficient because we're not computing everything all at once. I mean, I guess actually the benchmark was not faster. Indices. I see. copy is like fine too, actually. We really just only changing insert. Actually, in that case, we can just combine the two of this. Because copy is like pretty fast. Like the only thing that you actually cache is like feeding forward through the actual network, I guess. So that happens in sub too. So I'm actually okay with we predict the new edits. During inference. Yeah, I mean, we always get all the edits on parallel anyways. And we just index for the relevant ones here. I think when that happens. And this is like fine because we're just copying the same embedding over and over again, I guess. Like, I guess we could change that, but yeah. Okay, so you know what? I'm just going to actually modify this. sure my AirPods died.
Okay, probably gonna have to close this out soon, but insert here. What do up here? I as well, and then finally. Okay, so yeah, this makes sense. Kind of hate this code duplication, actually. This is gonna echo if I do this. I don't care. Actually, no, I'm sure that's bad. Self.forward with it's literally just this, right? Yeah, so initialize target is none, just the safe at first. Does this work? Okay, this works. I think I'm done with this fucking bullshit for now. Really not. Is this happening inside a cache block? Nope. Where is this happening? 147 here. Let's see. So forward with pre-target I.